Hello, so in this video I'm going to show you an example how we can express a problem using a Boolean expression and how we can simplify this expression to minimize the number of operator or the number of components if we want to actually implement to build the circuit of this expression using Boolean algebra. And first we need to know a couple of different Boolean algebra theorems and axioms. So there is the associativity and the commutativity that is common to the I'll say the regular algebra. The identity, if you have A or false, then the output is A. If you have A and true, the output is A. The complementarity, if you have A or not A, one of the two has to be false and one of the two has to be true, so the output is true. And if you have A and not A, one of the two has to be false, one of the two has to be true, so the output is false. The one we're going to use a lot are the one from the distributivity. So A and B or C is the same as A and B or A and C. And A or B and C is the same as A or B and A or C. Another couple of theorems. A or A and B is A, and A and A or B is A, and we're going actually to prove that. And the De Morgan theorems, when you can split, let's say, negation or merge negation. So to prove that A or A and B equals A and A or B, the first thing we can do here is A is the same as A or A, and we can get the same thing, A and B. And here we see that we can use the distributivity to write A and A or B, and that's it. And now to prove that this is equals to A, then we can write that this is equal to A and A or B. That's what we just proved. And then A is the same as A and true, and or A and B. And now you see that we can factorize by A and 1 or B, and true or B is true. So this is equals to A, and that's it. Now let's take a problem, the following problem. So let's say that Dr. Grumpy wants to drink his tea with lemon and honey, or mint and sugar, or lemon and sugar, or mint and honey. So we have 2 to the power of different possible combination, and we're going to write them all in a truth table. So no lemon, no honey, no mint, no sugar, and the output is no, Dr. Grumpy is not going to drink his tea like this. If there is a no lemon, no honey, no mint, and sugar, no is not going to drink his tea. If there is no lemon, no honey, mint, no sugar, no is not going to drink his tea. If there is no lemon, no honey, mint, and sugar, yes, that's one of the conditions stated above, so he's going to drink his tea. No lemon, honey, no mint, and no sugar, no is not going to drink his tea. No lemon, honey, no mint, and sugar, no is not going to drink his tea. No lemon, honey, mint, and no sugar, yes, it's one of the conditions stated above, so he's going to drink his tea. No lemon, honey, mint, and sugar, no, it's not, that's too much. Lemon, this time, no honey, no mint, and no sugar, no is not going to drink his tea. Lemon, no honey, no mint, and sugar, yes, that's one of the conditions stated above, so he's going to drink his tea. Lemon, no honey, mint, and no sugar, no, is not going to drink his tea. Lemon, no honey, mint, and sugar, no, is not going to drink his tea. Lemon, no honey, no mint, and honey and no sugar, so yes, is going to drink his tea. And we have lemon, honey, no mint, and sugar, so no, that's too much, he's not going to drink his tea. And last one, lemon, honey, mint, and no sugar. That's not the last one, so he's not going to drink his tea, and that's the last one. So lemon, honey, mint, and sugar. So no, he's not going to drink his tea. So that's too much stuff in tea. That's not good. So now that we have this, for each row where the output is true, here we have one here. Then we can see what are the conditions on the left-hand side of the truth table. So that's no lemon, no honey, mint, and sugar. So that's not A, not B, C, and D. And we do the same for every row where the output is true. So here we have not A, B, C, and not D. Here we have A, because there's lemon, not B, we have not C, and we have D. And last one here, we have A, B, not C, and not D. And the Boolean expression that is going to answer the question if Dr. Wimp is going to drink his tea knowing A, B, and C, D is the following. It's the disjunction of all this conjunction. And now we can simplify this expression. So here I'm using the distributivity to factorize by not A and C. As you can see here, we have two expressions where we have not A and C. So it makes not A and C and not B and D, or B and not D. And we do the same here with A and not C, all right? So we have A and not C, and not B and D, or B and not D. And here we'll recognize actually that we have something. This expression here is exclusive OR, which I'll write X equals B XOR exclusive OR D. And here we have the same thing here, so we have X again. And now you can see here that we have not A and C here, and A and not C here. And if I call that Y, and this Z, then we have Y and X, or Z or X, all right? Now, let's write this down. So Y and X, or Z and X, Y and X, or Z or X. And we can use distributivity again here to factorize by X. So we have X and Y or Z. So if I write this down using the full expression, we have B XOR D, that's my X, and Y, that's my not A and C, or A and not C, that's my Z. And here you recognize another exclusive OR. We have A XOR C. And I think we're done here. So the solution, the simplified expression for this Boolean expression is B XOR D and A XOR C. So XOR is the sign of XOR is a plus, a circled plus. And there you go. Now we're going to draw the circuit for this expression. So you remember the exclusive OR looks like an OR. For the sample, it's like a crescent with a double bar. So we have A XOR C here. And now we'll do B XOR D there. And then the output is the first thing and the second thing. So the output of the first thing, the XOR C, and the output of the B XOR D. And that's our circuit. That is going to be true when Dr. Grumpy is going to drink his tea, and false otherwise, according to the condition we stated.